Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 53 and we will be looking at the single qubit system for this lecture. The outline of this lecture will be, let's look at a single qubit operation, the key components, how do you control the qubits, what is the meaning of Bloch sphere, execution of the single qubit gates, control circuitry component, and then various advancement in this approach of controlling and executing of a single qubit. Now, we have already studied the architecture of controller and we have seen in our previous discussion that generally to control the readout or the state of the qubit, we either use a microwave signal or an optical signal, right. So, there are two types of signals which are provided and these are actually given here as microwave signal here and optical signal, right. So, optical signal will go through the avalanche photodetector here and then through a amplifier. Microwave signal will go through a low noise amplifier, mixer and so on and so forth. The final result is you need to be very cautious that while crossing these active devices, you do not add noise to the signal to a larger extent. So, that is one important point. So, to manipulate the qubits, we generate some very short burst microwave pulses, right, are applied, and these are typically 1 microsecond, they last for approximately 1 microsecond. These are relatively high frequency, somewhere in the range of, for transmons, which is a type of a superconducting qubit where you operate at a very low temperature, the microwave bursts range in the order of 4 to 8 gigahertz, whereas if you are spin qubits, they generally occur at much higher frequency of 12 gigahertz. This is the input frequency of the microwave signal which you are inserting to change the state or to read the state of the qubit without destroying its coherency is required. Now, let us look at the single qubit operation. This is basically refers to any unitary transformation which we have studied earlier if you apply to the state of a single qubit, right. So, if you want to do a superposition, you are doing a manipulation of the state on a single qubit, then we define that to be as a single qubit operation and we generally do an unitary transformation on that. Now, these operations are represented mathematically by matrices which we have studied earlier and this qubit state vectors in a two-dimensional Hilbert space. Even if you do not understand two-dimensional Hilbert space, you must understand that for the state of a qubit when you are actually trying to do a mathematical analysis can be represented by a matrices, and there are, when you manipulate it within x, y, z gates and Hadamard gate or even Toffoli gate or phase gates, there is a matrix associated with that. So, it is basically a matrix multiplication operation for any of the gates which you design. So, let us say that so the basic qubit operation will include these steps which you see in below. You will have an initialization, which means that you need to prepare the qubit in a known state, right. Let us say in this case typically 0 ket I am doing it. So, I very well know that what is the initial. So, the initial state is a known state to me for all practical purposes, right. Now, manipulation means basically changing the qubit state using quantum gates, which is basically Pauli gate X, Y, Z, which we have already studied earlier, and Hadamard and phase gates S and T, right. And this will result in rotation about the arbitrary axis. So, if there is an arbitrary axis across which the initialization has been done by application of these gates, you will be able to rotate it either clockwise or anti-clockwise and so on and so forth. Now, measurement is quite an interesting one. Measurement is basically you want to collapse the qubit into a classical bit by measurement. What does it mean? It effectively means that when it is in a quantum state, you are not aware of its exact value, but when you convert this into using proper measurement, when you convert this into a classical bit, its value is well known to you for all practical purposes. The measurement value is what we do when we do a single bit operation. Let us look at a basic single qubit operation. Now, as I discussed with you, it is rotation around XYZ axis. So, let us suppose I will discuss the Bloch sphere, but nonetheless we can discuss here X, Y and Z, right. Now, across this axis the matrix can be rotated, right, in a clockwise or in an anti-clockwise, clockwise or in an anti-clockwise manner. This is anti-clockwise and this is clockwise, right. For example, if you take an X gate and you apply Pauli X gate and you apply this flip, it will flip 0 to 1, right. and it will be rotated around the x axis, right. There will be a pi rotation and a 0 will be flipped to 1. So, a 0 basically flips to 1. Now, how do you visualize it is using a Bloch sphere. We will learn that as we move along. But how are these rotations performed? We use the microwave pulses, which I discussed with you in the earlier slide, 12 gigahertz for spin qubits and 8 to 10 gigahertz for, or maybe 4 to 8 gigahertz for transmons, which are superconducting qubits. What you do, you generate microwave pulses and they help you to enact these rotations. Now, the duration and the phase of the pulse determine the rotation of the angle and the axis. So, how much time you are giving for how many microseconds and what is the phase of the pulse will actually determine the phase will determine the rotation of the angle. Now, the phase diagram, if you want to have an RF microwave pulse, you can apply it to a qubit for doing it. Now, why control single qubits, right? First is precision and individuality. Precision means the controlling single qubits allows for precision manipulation of each qubit state. And this is very important, that there can be multiple qubits on the platform which is sitting at the qubit end, maybe a transmon or a spin qubit. However, the microwave pulses are very directed and a very precise control can be done on a single qubit without even interfering into the other qubits. So, the interferences are very small, and that is what is written here, that without affecting others, and this is very essential for accurate quantum operations, right. It is quite important for accurate quantum operations as such. Now, implementation of quantum algorithm, right. Many quantum algorithm require the ability to perform specific gate operations on individual gates, right, and therefore, you can actually use exclusive quantum algorithms for implementation of these microwave pulses. The third point is error correction and mitigation. Now, if you are able to do a targeted control, your error corrections are done in a much more efficient manner, and then and therefore, you do a very specific change in the error correction rather than generalizing the error correction node. So, that is what is written here, that by addressing specific qubits to detect and correct the errors, right. Now, if you prepare the initial states, which we have done already, and we perform the performing measurements, then single qubit for high fidelity. So, I just want to control a single qubit without affecting the states. Quantum algorithms can be applied, error correction is more directed, and the state preparation and measurement gives you high fidelity. The third point, the last 3 points are flexibility and compatibility. Now, when you are able to control a single qubit, you can always understand that it gives you flexibility in circuit design, and it enables complex gate sequences. Why? Because if there are 4 qubits and if I can manipulate 4 qubits on an individual scale, right, I will be able to control the circuit in a much better manner, and therefore, these are qubit specific operations. If you look at testing and calibration, well, testing and calibration, then basically precise control on individual qubit is important, right, and this is crucial for calibrating the devices, right, and testing quantum hardware performances. So, testing and calibration is an important part. The second last point is basically, if you focused control is there will be unwanted interactions and the crosstalks between qubits will be minimized, and therefore, the overall system accuracy and fidelity will be improved, right. So, this will be improved to a larger extent. So, we have learned why single qubit control is important. So, one of the major challenges of any quantum systems are that the readout circuitry should be able to actually control qubits on an individual level without affecting the nearby qubits, right, and that is quite important and essential. To understand that, let us have a Bloch sphere understanding. So, I can say that, as I discussed with you, that a qubit is either a superposition of 0 and 1 with weights associated with it. So, basically alpha times 0, beta times 1, which means that if the 0 states gets gain, alpha will be very large, and if 1 state wants to get gain, beta will be very large. So, a Bloch sphere is primarily a geometrical visualization, and they represent the qubit in a geometrical form. So, Bloch sphere, if you see, this is x, y and z axis, the 3-dimensional plane which you get, and this is basically the qubit which I am representing. It is at an angle of theta with y axis, phi with your with the xz plane. Xz plane, it is approximately equals to y. So, this is your xz plane, and this is phi which you set, right. And if you look at the overall issue here, then this is 1, we refer to this as 1 and this to be as 0 state, initial 0 state. So, Bloch sphere edge is my 0 state. So, what I say is basically the Bloch sphere has a radius of 1. So if this is basically 1, we get the overall distance between any 2 points within the Bloch sphere to be equals to √2, and that is the reason this comes in the denominator as √2. So, effectively if you take 0 plus 1 by √2, so we get alpha 0 plus beta 1 divided by √2 happens to be the Bloch sphere. So now if you want to rotate so you want to do transformation from say 0 to 1, let us suppose here you want to transform, right, one scale, then we can do a transformation by applying either an X gate or a X gate generally is applied. So, 0 to 1. So, any point on the surface of the Bloch sphere will represent a superposition state, right, and superposition is defined by 2 angles theta and phi as I discussed with you, and these are the spherical coordinate system which is there. So, we have here theta and phi. Depending upon this 3 coordinate system, this gives you an idea, which means that Bloch sphere is basically a visual method to understand the quantum states and its operation. Now, how does it help me? It helps me to, the Bloch sphere helps me to simplify the abstract behavior of qubit. So, visualizing the qubit is an important point, and that is done using Bloch sphere. So, the surface of the Bloch sphere, as you can see, this point blue colored and red colored are basically 0 state and 1 state which I am doing. Any state in between will be a superposition of 1 and 0. This is pure 0, this is pure 1. Any on this plate or this axis will be basically a superposition of 0 state and 1 state. So, Bloch sphere is a visual representation of the logic. Now, execution of a single qubit gate. Now, executing a single qubit operation will involve therefore a very well defined controls pulse signal. In this case, we are assuming microwave, we are not doing optical at this stage, and this will cause the qubit state to evolve using certain unitary transformations. So, first thing is rotation. Rotation is done by through x, y, z gates, and you will get, for example, rx theta, ry theta and rz theta. Now, if you apply a specific microwave pulse with specific amplitude, phase and duration, you will be able to do a change in the state of the qubit, and not only state of the qubit, but you can do a pi by 2 shift or 3 pi by 2 shift and so on and so forth. For example, let me give an example. A pi by 2 shift around x axis a pi by 2 shift around x axis corresponds to actually 90-degree rotation, and this transforms the 0 state towards a superposition state. Superposition means it is superposition now of 0 and 1 state. So, how do I do it? By applying a particular gate to the state, qubit state, and it will be able to convert from 0 state towards a superposition state of 0 and 1. Now, as I discussed with you, precise calibration of the duration of and phase is critical, and slight deviation can cause a large amount of gate error, right. And therefore, as I discussed with you earlier, and that is where the whole topic of this lecture is, that the cryogenic control circuits actually tend to minimize the noise and improve the fidelity control of the operation, and therefore more precise operation can be done. And if there is a small amount of noise being introduced, what happens is that the rotation will not be perfect to pi by 2, and therefore the superposition state, which a priori is determined by the superposition of a 0 state and 1 state, will not hold good for these purposes. Now, in cryogenic environment, the classical control circuitry designed to perform these are RF oscillators, mixers and modulators and pulse generators, right. RF oscillators, as you very well know, they will generate precise frequencies of and phase of certain RF signals from 4 to 8 gigahertz or 12 gigahertz. What is the requirement for mixers and modulators? They are primarily used to shape and modulate the signal for specific rotation angles. So, if my rotation angle is not pi by 2, but something else, then mixers and modulators will be helping to shape and modulate the signal, right. What are pulse generators? These are accurate microwave RF pulses to execute the quantum gates. So all these 3 are quite important, and please understand all these 3 gates are actually sitting at cryogenic temperatures, at very low temperatures, right. Then the next is low noise amplifiers, which are basically sense weak signals during readout, and therefore are crucial for feedback calibration during control. Timing and synchronization, we need to also be careful that the pulses which are generated should be synchronous with respect to some external clock. Otherwise, we won't be able to control all the other qubits in sequence or in combination, right? And therefore, the external output which will be a linear superposition of all the qubit states will not be proper, because each states have actually given an error to it because of non-accurate timing or synchronization circuitry. Now, what is the role of the classical controller? Classical controller will generate control, timing signals, process readout circuit and implement error execution, and it will primarily sit at room temperature and communicate with cryogenic qubit at a much lower temperature. The standard approach was that control was done sequentially. So it's basically control was done in a sequential manner, one after other, and therefore it was slightly slow, much slower, and then prone to error because of heavy noise associated with it. The calibrations which were initially done was not proper, and finally there will be large, if you do the conventional method, there will be large crosstalk, error accumulation, and limited scalability will be there when you do a standard approach. Now, so what we do is the complex gates are broken into sequence of simple operations, so pi by 2 or pi pulse, and this decomposition makes the precise control feasible, right. I will give you an example of that. Let us take Hadamard gate. It can be built from the rotation of X and Y gate, poly X gate and poly Y gate, right, and these basic gates are like building blocks for the qubits. Now, let us finally come to the final part of the discussion here, that if I have a single qubit control qubit using an external voltage source, and what I do is I have, if you look at these are the two configurable qubits, coupling qubits, right. Part A is, if you look, part A is this one, this is part A. The coupler MT is on, right, the empty coupler is on and MB is off, let us suppose, which is this one. And therefore, only you see, only though you are getting the input, only the top qubit is driven. The bottom qubit is almost flat, you see. This crossover is to show that so I am doing operation of inversion. So I am doing an operation of inversion in the sense that a crossover is happening in the control qubit state. Similarly, if you look at figure number B here, then the coupler MT is off and MB is on, and only the bottom qubit QB is driven. So the coupler helps you to pass on the input signal to a specific qubit, right, and this helps you to control the qubit in a proper sense. And so if you look at the left hand side diagram here, these are the population probability here. So this is leakage. The leakage probability goes on increasing, and it remains constant when it is undriven in state, but when it is driven in state, leakage probability goes on increasing, both for this case, QB case, as well as for QT state. So this is the top is the QT state and the bottom is a QB state, right. And as you can see, in the case of undriven, the probability of occupancy or population is very low. It goes suddenly low at very large number of gates. What we are doing is we are comparing that with the number of Clifford gate. So these are one type of, at this stage don't worry, these are some types of gates. As the number of gates goes on increasing, the leakage current increases whenever your QT is driven, right, but your undriven state has got no influence. The probability of population is always 1 here. This gives you a basic example that by doing proper manipulation of the control qubit, I can actually drive individual qubits by an external source. And not only that, what I am showing you here is we are actually preventing an crosstalk, right. I do not want the crosstalk to happen in this case. Let us come to, if you come to C and D, which is this one here, then so the P0 is basically my probability that the qubit is in the ground state 0, P1 is the probability of being excited to one state, and probability of being in non-computational state. When I say non-computational state, it primarily means that indeterministic state, and that is referred to as a leakage state. So if you look at QT and QB, both the diagrams, the driven state has got relatively a larger probability, right. So the P0 is, this is P0, right, this is P0, this is P1, P2. So this is your lower one, this is P2 here, right? This is P2 here, and this is P1 here, and this is your P0. So if you look very carefully on QT, which is the driven state, then P0 in the ground state probability is relatively high. Probability of an excited state 1 is, so they are coming to 0.5 around, approximately at 0.5 for large number of gates. However, the driven one, or the probability of a non-computational state, which is a leakage state, is relatively much lower, right? And that shows to you the fidelity of the readout circuitry. Now, as I discussed with you, as you apply more and more gates, the P0 decreases and P1 increases, right, indicating a transition between 0 and 1. I hope you get the point, because P0 decreases means the more and more transition happens between 0th states to 1 state, and that is shown here, right. The 1 state is increasing and the 0th state is decreasing. P2 is increasing because there is some leakages happening even at 2 state. So, if you see, this is almost constant and almost in the 0 range region, both the cases. In both the cases for QB and QT, when QT is driven and QB is driven, the 1 state is going down around 0.5 and 1 state is going up around 0.5. If you further increase it, you will see a crossover and the 1 state will go to the driven state. If you look at the leakage analysis, just leakage analysis, we have expanded the y-axis here. For P2, the y-axis has been expanded, right, and therefore you see this whole thing has been expanded from 0 to 0.06. And there is a slight increase of these leakage currents or leakage gates or these leakages with the number of Clifford gates. So, if the number of gates are increasing, there is a small increase which is happening here. Leakage is low, but nonetheless its probability is so small that I have a much robust qubit control for P1 and P2. And that is the advantage of a single qubit control of VSM. Now, if you look at the undriven qubit response, for example, when you look at this figure and this figure, then if stays in the ground state where the Alder is being driven, then P0 remains close to 1. You see, this P0 remains close to 1, and therefore there is a minimal crosstalk, which means that I am not interfering with one state, right? And that's what was my initial assumption, that if you want to have a readout circuitry, it cannot interfere with nearby qubits, right. For the undriven state, leakage state, this value for the undriven state, it falls down drastically with Clifford gate and remains almost stable after that, because this shows the highest fidelity for the qubit control using an external logic signal. So, let us summarize basically the single qubit operation. Again, the same graph is shown here, but we have obtained high fidelity gate operation. We obtain high fidelity gate operation. The leakage is relatively very low in this case, and we have been able to suppress the clock, right. So, this is important for scalable computing, which basically means that if you start with 2 qubit, go to 4 qubit, 8, 16 and so on and so forth, I am still able to do high fidelity such that all the qubits can be controlled by the readout circuit individually, right, and that gives you the scalability in quantum computing, right. Okay. So, the global broadcasting technique is that there is endless sort of enables simultaneous application of control pulses to multiple qubits, and you achieve it through a single control pulse channel and simplifying the control hardware setup, right. So, if you do a global broadcasting technique, is that you use a single hardware setup to control it, and it achieves parallelism, right, across all the qubits in multi-qubit systems. So, if you have multi-qubit systems, each control readout controls each of the qubits, and which effectively means that I can control all of them individually by external power source. Now, this reduces the complexity of wiring and control electronics, but obvious, and therefore independent of qubit manipulation, you can control the overall system. Advantage: operational efficiency is much higher, and you will have much reduced overall gate operations. So, let us summarize the main points which you see here, that this is a single bit we have controlled it. We have been controlling using either microwave pulses or optical pulses. We looked into the challenges, errors and crosstalks. We looked into the Bloch sphere model, and once we looked into the Bloch sphere model, we also looked into how the Bloch sphere represents 0 state and a 1 state, and how a 0 state to 1 state and 1 to 0 state is manipulated by application of external gate. Finally, when we were explaining to you the concept of cross coupled state, we saw that the driven state and undriven state can be separated very easily. That gives you fidelity, and the error is minimized in such a scenario. So, I have given you a brief idea, and then we finally ended up with giving you a recent scenario of the global broadcast technique. So, with this we have been able to give you a brief idea or brief concept of the single qubit control system. I hope you enjoyed the lecture. Till we meet next time, goodbye.